I go by Hermanus or Herman. I'll respond to any of those for questions. And thank you so much, everyone, for all the effort you put in, especially my examiners. I really, really appreciate the feedback. It's been exceptionally useful. One of the things that we identified as a key interest for flame retardants is the mining industry. The key reasons for this is that there is an exceptionally large amount of piping and other plastic materials that are used in mines. On this slide, you'll see Tuatona gold mine, which is the deepest gold mine in the world at 3.9 kilometers. And one of the things, as I go to slide 3, you'll notice is there are a lot of battery boxes and other plastic materials that in these small conditions could be exposed to flame and would have very negative repercussions. So these battery casings are injection molded and some of the battery boxes are rotor molded. What one needs is a material that can be both extruded or injection molded or processed in many different methods. One of the reasons that it's so very important to flame retard in these conditions is that they're in very small spaces and getting the people evacuated is exceptionally difficult. These space conditions are analogous to those in diving submarines, and in fact, these mines use similar fire testing specifications to those type of situations because every second really, really counts. One of the things that they want, especially in mining conditions, is they want polyethylene components, but they want them to have a few different specific effects that they can deliver. Here you'll see that needs to be cost effective because otherwise it won't be implemented to the scale that would be ideal. Anti-static because static would be a really, really big problem. Flame retarded, have enhanced thermal conductivity and suitable for processing through multiple methods. So one of the very nice things about expandable graphite, and that is why we identified it to begin with, was that previous studies prior to the start of my studies at the University of Pretoria proved that there are anti-static and thermal conductivity abilities that can be achieved through the use of expanded or expandable graphite. Flame retardation, once again, is also one of its key facets. For a fire, there is a few different mechanisms. There is a fire triangle, meaning for a fire to exist, all three of these are required: material, oxygen, heat. In the real fire, however, there's a lot more complex phenomena that interact. One of those is heat transfer and the heat load, and that has a substantial effect on the fire growth and the fire spread and how quickly it flashes over and smoke reaches the point where smoke inhalation would be poisonous. So for this reason, there are multiple different flame retardation mechanisms that are used to counteract this sort of rapid fire growth. So one of those is endothermic degradation, where energy is taken away from the flame. Another is gas radical quenching, which is one that stops a lot of the oxidation that starts breaking it down. And then there's obviously dilution of the gas phase and thermal shielding. So those last two are of key interest to us because those are ones that expandable graphite and especially intermittent flame retardants deliver a really good result with by making a thermal barrier, and then often to make that thermal barrier, gas is released which expands that outer layer, and that thermal shielding then does both phases, blocking some of the oxygen transfer, but also some of the heat transfer due to the thermal shielding. One of the big desires with a sort of well flame retarded versus a non-well flame retarded material is that the longer you can delay ignition and the lower your heat release rate over time is, and the slower you reach your peak heat release, the better it would be for the people who are trying to escape. Because the final target ultimately of all fire retardants is to allow time for people to come, but also for extinguishing to occur with the help of the fire department. So we identified expandable graphite because in a low loading at 10%, it's able to meet the UL 94 V0 international rating, which gives a very good indication on a small scale of some of the fire performance. But one of the things that we found in our earlier scoping research is that when this material at 10% load is put into a very large scale, into a pallet, a plastic pallet, and burnt, that there are actually some negative effects as well. So what we want from it is uniform fire performance, but unfortunately initially it did not deliver that. One of the reasons for that is that as it expands, it creates strings, and these strings, when attacked from above, go out and then lay down on the material, making a thermal shield. They also make a good barrier from the side by falling against the material. But from below, there are very negative gravitational effects whereby the weight of the hanging expandable graphite strings actually pulls open more of the polymeric material, actually feeding the flame further. So in some cases, it actually had worse performance from below than unflame retardant polyethylene. So one of the reasons we really wanted to improve this was that expandable graphite is a relatively low cost flame retardant. I've spoken about the negatives. Now, what can we do to fix those? A lot of the earlier studies, they've found that graphite intercalation compounds, that co-intercalation can be done, and that there are, for instance, a few boric acid and sulfuric acid based mixtures that can co-intercalate. But the reason we didn't want to make the expandable graphite from scratch is that there is already this really inexpensive industrial product produced at a very large scale. So one of the first avenues of research we took was to attempt to modify this expandable graphite through ion exchange. So that had a two-pronged reason for that approach. One reason was that by attempting to wash and ion exchange, we can get an indication of how loosely or solidly bonded the sulfate ions on the inside of expandable graphite are, and we could potentially put other ions in. One of the ions we identified was boron, which has a low glass transition. We surmised that if one could intercalate this through an ion exchange into the center of the graphitic structure, that as it expands, it would become a sticky string that would stick to one another. Unfortunately, this was unsuccessful, but we had another card up our sleeves. So we decided to look at testing binary systems. So for the binary systems, one of our first materials considered was ethylene diamine phosphate. The reason for this is that there were a couple small studies that had been done before I started the research way back. And those indicated that together with expandable graphite, that does show some interesting results. What we wanted to avoid, though, are the negatives of ethylene diamine phosphate. Those being that it is a very expensive material and it requires, unless it's a spray coating, if it's put through the entire material, it's quite a high loading in order to meet a UL 94 V0 and good cone calorimeter results. The final and actually also very key thing is that it releases smoke that then sort of further exacerbates the problem in these small enclosed spaces. Now, together with this material, we also theorized that we could make a novel flame retardant. So I'll get back to that one in a bit. Our main material is expandable graphite on the next slide. And what you'll see here is that I actually took SEM micrographs, about 15, 20 SEM micrographs of expandable graphite after it had expanded. And this gives a very, very good indication of just how explosive that exfoliation event is. One of the things you'll notice on the bottom left is that the general belief before we started our study was that it would be a pure intercalated material. There'd be intercalated molecules of SO4 in between the interstratified in between the layers, and that those would simply release SO2 gas, causing this expansion. One of the things that we discovered, however, was through analysis of these two different materials, although they look very similar on the surface, they have very, very different structures actually. So one of the reasons for this is that what we identified, as you'll find in my thesis, is that the low temperature onset expansion material actually is not as pure a intercalated compound as the other. What it has undergone is an even more excessive level of oxidation. And we determined that that was due to KMNO4 used as a very strong oxidant at the start of the intercalation process. So what this caused is that this material actually has a lot higher oxide or oxygen to sulfur ratio, which has some positive results in that it expands even more explosively, as I'll show you soon. I put up the TMA results for these two materials. You'll notice they have very different onset temperatures. So this is as a direct result of that overoxidation that caused some of the layers to actually become further oxidized, having a lot of different other oxygen groups, which then release even more oxygen. But as an effect of that, it's a less thermally stable product. So this graphitic structure is not as stable as natural graphite or natural graphite with very even distribution of intercalated molecules. And one of the things that we noticed is, as you'll see with expandable graphite here, it almost doubles the amount of expansion of ES170, the high expansion onset material, because there is a 27 times higher sulfur to oxygen ratio in this material, meaning there's a lot of other extra oxygen and CO2 gases that get released in addition to the SO2 naturally released from expandable graphite, which have some really positive results actually if one desires to flame retard at that onset temperature. I'll be quick with the next slide. The next slide was ethylene diamine phosphate. We assessed our laboratory produced product against industrially produced product. And through Raman and FTIR, you can see here that very, very similar results were found and that our product was thus extremely pure. This was really just a quality check for us so that we know that this is a highly crystalline material, that our peaks are high on XRD, and that we have a good crystallinity, a good yield, and that it follows a similar structure to that of the industrially produced product. Here is where I talk about the novel product we designed. So one of the reasons that we theorized the production of this material we call 3,5-diamino benzoic acid phosphate is that this material that it's made from, diaminobenzoic acid, in a study quite a while back was used at the University of Pretoria as a filler in some polymeric material and seemed to have some naturally flame retarding abilities. We then combined this with the general thinking that phosphate groups cause very good intermeshing behavior. Let's see if we can do a little experiment and see if it works. Treat this benzoic acid with hydrochloric acid to oxidize it, and then treat it with ammonium dihydrogen phosphate in order to move a phosphate group onto the chain. And we actually succeeded in this, and our analysis through FTIR showed that all our expected amine groups, aromatic and primary amine groups, and the ammonium ion were found as we expected. We also assessed it through XOD and a few different methods, including SEM, where we could see that this product was highly crystalline. The next slide is which materials we used in terms of the combo black and the injection molding grade LDPE. But what's of key interest here is that this injection molding grade LDPE is an exceptionally low fire resistant material. This actually burns a lot more readily than most LDPEs, and when it's exposed, for instance, to cone calorimetry, there is very quick and even pyrolysis of the entire material. The first thing we did is we wanted to identify what compounds can we test. So if we want to actually find a material that is both better than expandable graphite on its own, or the two other intermesums on their own, but also which is more economically viable or economically interesting, we would need to go to smaller loading. So we took a 10 to 10 and 10 to 20 ratio mixture of the two materials so that we could test it and find whether even at 10 to 10 loading, maybe we can succeed. And if we do, in terms of delivering the flame retardants we need, that we could use this material as a very, very viable commercial alternative. So we looked at the thermal behaviors in TGA and in TMA of a lot of these materials. Unfortunately, EDAP was not one of the materials that we could do TMA analysis on because with thermomechanical analysis, the probe in this case would go into a softening or expanding event depending on the atmosphere that it's in. But that ethylene diamine phosphate becomes extremely glossy and it would actually damage the probe. So unfortunately, we couldn't do that, but we did verify with a few other methods that it would work in terms of reacting at the same time as expandable graphite so that their layers can expand into one another. So here I'll show you two of the SEM micrographs that we took. The two above and two below are distinctly different. You'll see that there are very sharp edges in the two below SEM micrographs, whereas the ones at the top have a round edge behavior. This is actually exactly what we wanted because the bottom one is pure expandable graphite and the top two micrographs show the glossy coating that this expandable graphite has gotten all over every little bit of its surface, even on this minor scale, which give it a bit more sticky, cohesive structure. So for the next compound, we did a similar thing, but here we could actually look at the TMA. So as you can see here on the right, you'll find that the softening event of diaminobenzoic phosphate, it occurs at a temperature of 257 degrees, and that this is actually before expandable graphite, even the low temperature expandable graphite expands, which is actually exactly what we want, because this would mean that once that material has softened, as the expansion event occurs, all of that material expands through the DABAP and then gives this cohesive thermal barrier. So here you'll see we did a similar check. On the right is the clean material, and on the left you see thoroughly coated once it's exposed in combination to an open flame. As I talk about the methods, I'll mention why each is used. In order to truly assess a material for every scale of use, one needs to assess it at a small, medium, and large scale. Now, this is because a lot of the behaviors on each of these scales are very different. This is why it's exceptionally important to put a lot of information about how one measures certain fire behavior, because your fire behavior, your fire retardance that you measure is very specific to those conditions. And that's why it's good to measure in as many different ways, in as many different conditions as possible, that are analogous to those that it would meet in real life. So cone calorimeter is really the big thing in fire testing. Cone calorimetry is an extremely robust method in that it allows simultaneous measurement of a very large amount of information. It actually simulates developing fires as they've sort of just started reaching developed and are continuing. So it is sort of a medium scale test. Our other method that we identified, which was one that we actually, people in our group invented, was to do a TGA coupled laser pyrolysis, which what this basically boils down to is that we can use extremely small samples, similar to those that one can usually analyze in analytical equipment, of 40 milligrams, and we can get an indication of, on a small scale, of what sort of charring, barrier effect, or mass loss effects occur which gives a very good indication of some of what one can expect in the larger scale tests such as cone calorimetry or open flame tests. So this is sort of a micro scale test, and we set the laser that we expose it to have a 5-watt power setting, which corresponds to 50 kilowatt per meter squared, which is a very, very well developed large scale flame. So we really put it to the test. And I'll get to the results on that a bit later. So the next thing that we wanted to do is we wanted to have something in between those two tests. So we had developed an open flame fire testing method, which is coupled with infrared data. So one will see there's a infrared camera that we used here. If that is angled at 45 degrees to the flame that is exposed to the material, that then keeps that infrared camera safe, but then can give you a plethora of information in terms of the thermal behavior during the entire thermal event of open flame exposure. So what we wanted to identify with the open flame tests, specifically, have we actually succeeded in improving on the goal of fixing expandable graphite's thermal shielding behavior from below? Or do those gravitational effects still have a very negative effect? So I'll get some videos soon that'll show what we found with that. But what we also could do in this case is we could expose the material from the side. And as one sees here in the horizontal exposure, which is from the side, that we could actually simulate a material where the flame has started on the floor and is now starting to touch the side of it, so that we can get an indication of whether there is melting, whether there is flow of the media, whether it actually ignites, and a lot of other such interesting results. The next slide, once again, is just how we made the materials. But what I want to highlight here is with the injection molding, we actually specifically decided to use a very generalized ASTM D5420 drop impact test disc mold to produce our open flame fire testing samples. So the benefit of this is that any university around the world that does mechanical testing on plastic materials will generally have this mold. And this test can thus be used anywhere to assess different materials against each other. This is a very robust test that would allow, at a very cheap level, to test materials. These two tests, the laser and the open flame fire testing, what we theorize is that they would allow us to rapid prototype and test multiple different materials, and then we could take those to the cone calorimeter to see how they really do in a proper test once we know they already deliver some good behavior. We set some success criteria for this. So for the open flame test, we wanted to increase our ignition delay, and we wanted to deliver that cohesive uniform fire barrier from below. For the cone calorimetry, we wanted to have a lower peak heat release, and we wanted to have the heat release travel more over a longer period of time, which by plateauing and making thermally thick thermal behavior to fire testing instead of thermally thin behavior, this actually allows for a much longer burn cycle, which allows, once again, time to evacuate and time to stop the fire due to intervention. On the laser pyrolysis side, we wanted to look specifically on for decreased mass loss rate, because if on that small scale where it's exposed to direct laser pyrolysis, this simulates the charring and the thermal behavior and the thermal shielding very well, which we actually succeeded quite well with in our materials. Here are some of our results. The cone calorimeter, one of the first things that we looked at was heat release rate. So the neat material, which was not flame retardant, you'll notice here has a very sharp peak. And it's also much, much, much higher than the others. And this peak is actually around 710 kilowatts per meter squared, which is what we generally expected for polyethylene. But it's not a very, very good result. However, once we add these flame retardants you can see that they are substantially lower and longer thermal graphs, and that they do not reach the same sort of peak. The standalone materials manage to go between 300 and 400 kilowatts per meter squared, which is about a third of the initial peak, whereas the combinations then went even lower, taking it as low as 250 kilowatts per meter squared, which was a very, very good result. Now, this actually shows it quite a bit better. So what you'll see here is that each of these lines represent one of our mixtures. So ES250 is the low temperature. So the first two on the right are the low temperature expandable graphite mixed with EDAP and DABAP respectively, whereas the rear two are for the higher onset temperature material. So one of the things that we can see here is that it sort of moves down in a wave to the bottom, and it shows really good results in the two yellow samples, which is actually exactly what we wanted, because you'll notice that those, they say 10 and 10 and 10 and 20 next to them, are actually our combined formulations. And those formulations are the ones that are actually the most economically favorable. So we actually achieved some really good results here, in that all of these materials, when they're used together in a binary system, delivered thermal behavior that exceeded that of the material itself. The expandable graphite reduced the peak heat release by a substantial amount, and these intermescents in combination with that big reduction then proved even more effective. Although smoke release rate is not the sort of be-all and end-all of what one desires information on, as there are a lot of different factors involved. Smoke release is of key importance because as the flame becomes well developed, smoke release always occurs. And the slower that release can be, the less likely one is to reach toxicity such that the people are either unable to breathe or are in fact affected by the gas itself. So here you'll see in the total smoke release. So one of the interesting results we found here, which I suppose is to be expected, is that the intermescents, although because they're organic materials, actually seem to increase the smoke release quite substantially. But what we found was that expandable graphite in the 10-0 line, second from the right, was extremely effective as a smoke suppressant. So this was actually a bit of a best case scenario, because not only was it capable of suppressing that smoke quite substantially, but when we tested the materials in a binary system, although the organic materials do increase the smoke generation, in the binary systems it was still within a margin close to that of the original neat material. So that was quite a good result that we got. Now, with cone calorimetry, I can't unfortunately discuss all of the many results that we got, but two of the very interesting parameters that give a very good indication or comparison between different materials is called the FIGRA and the MARE parameter. So FIGRA gives an indication of the growth rate, or how quickly does the fire spread to increase its size, because the quicker it spreads, obviously, the worse it is. And once again, we found that really good result. We found that the neat materials improved the FIGRA, but that their combinations far exceeded those. In fact, so much that it really exceeded our expectation, leading us to think that it was somewhat of a synergistic effect between the two different intermessing behaviors. Because here at 10-10 loading, there is a lot less of the EDAP or of the DABAP, but they both improve upon any of the materials on their own. Now, on the MARE, we look at which is the tendency of a fire to develop. So it gives an indication of how quickly a fire will develop into a fully developed fire. So it is somewhat related to the heat release rate. So what it actually is it's the maximum average rate of heat emission. So Ma rate is the peak value of the ratio between the heat release rate over the time until it reaches that point. But what we found here, which was really, really great again, was that our combinations again exceeded our materials on their own. And that even at that smaller amount, the EDAP definitely contributed to all facets and the DABUP to all facets of the fire behavior of the material. So although there is a somewhat marginal increase in some of them, all of these factors, when taken together, make for a much, much improved result. So I'll go now to the video. What you'll see here is that for the open flame test, in order to develop this method, we tested at first just the low temperature expandable graphite together with each of the materials. So here you'll see on the left is the neat material, then EDAP on its own, expandable graphite, and then the combinations. And here I will indicate when their failure occurs. So the worst and the quickest via burn through was in the neat material. Whereas the second one, which actually started burning quite a bit, was the expandable graphite itself, because the strings are a bit more readily available to burn. But here in the other ones, there is some really good thermal behavior, such that in the eventual best products, only once the material reaches a melting temperature and sags does it actually undergo failure, and burn through does not actually occur. So I'll show that on the next slide. So we observed two mechanisms of failure, burn through and sag. And here we actually found that if it prevented burn through entirely until it was fully melted, that was actually a really, really good result, because it still maintained some of its structure up until that point and thus delivered some really good results. In all of these cases, once again, the binary systems really exceeded our expectations, giving some really good cohesive expansion and some good thermal barrier behavior. Now, one of the other things we looked at with the open flame fire testing is the time to ignition. And here you'll see that we actually had some where no ignition whatsoever occurred. And those are the binary systems of EDAP and expandable graphite. So this is a really, really great result, because what this means is that expandable graphite has changed completely from its base behavior, where it expands as these loose strings and that are readily available for attack, that even in the attack from below, in the middle here, that it could not actually ignite. Whereas in previous studies, expandable graphite always ignited, further fueling the flame, further causing those negative gravitational effects. So on the next slide, I'll show you guys the great result from below for the ethylene diamine. Expandable graphite on its own is on the left, and if you look closely, you'll see there are little particles flying around. These particles are expandable graphite pieces and pieces of material that are simply igniting and flying around and causing increased failure, whereas in the other materials, it almost looks like nothing's happening, but they've actually just continued burning until they eventually sag. And this is quite a good result, because the flame, although one can see the flame, never actually starts burning on the surface itself. So what are the conclusions that we could make from this? From this, we could see that in the vertical tests, all the flame retardants gave the improvement that we actually aimed for. All of them increased the ignition time and the burn through time, giving that valuable time for people to address the fire or escape. In the horizontal tests, we actually found that burn through is entirely blocked, and in some cases ignition as well, which is an exceptional result for this material, which previously could not achieve this result on its own. Now I'll move on to our laser pyrolysis. One of the things that we found of key interest with the laser pyrolysis is whether our curves will mirror those that we achieve in terms of mass loss from cone calorimetry. So here you can see that for the ES250, the low temperature expandable graphite, that in terms of residual mass, it showed some really good results. That the 10 weight percent expandable graphite on its own was not that much better than the neat material in a small scale pyrolysis test, but in the mixtures, in the binary systems, we achieved some exceptional results in that our mass loss actually went to only 20% from a previous point where it went to 5% or 10% remaining at the end of the entire thermal event. Here on the next slide shows an indication of, on the right, what the infrared camera itself actually picked up, and that is that here one can see that the overall temperature profile is much, much lower for especially the binary systems with EDAP and expandable graphite. In fact, it once again seems to indicate that there is a synergism of sorts in that it is lower than any of the individual materials are able, or any of our expected results if one quantified the results together. And this actually indicated, strangely enough, that the best temperature resistance was actually achieved in the 1010, which is actually our cheapest binary compound, which is a very, very good result. We were quite happy with that. Now we'll get to that comparison. Now, how does this weigh up against cone calorimetry? Because if we want to use this to inform our decisions so that we select good materials before we scale up to cone calorimeter testing, we need to find analogous results. We need to find results that mirror the same trends. And in fact, we found something interesting here. We found that on our small scale laser pyrolysis, we actually found a lot worse performance for the 10% expandable graphite material. And we believe that this is closely linked to its thermal behavior that we tried to address, in that it did not create a cohesive barrier, and that the laser energy that was transferred caused a very quick burn through of the strings as they came out, because they were not bonding to one another to block the thermal event. But outside of that, all of the trends are similar. The best result is still in the 1010 binary system, and the 1020 is second best. Once again, a really great result both in cone calorimetry and on the small scale, that our cheaper additive mixture was actually the better result. In conclusion, regarding the laser pyrolysis, here we've simulated the pyrolysis portion. It reaches that same rapid temperature rise and a quasi-steady state, and all flame retardants delivered good mass loss resistance. So this, I think, indicated to us that this is definitely a good method for testing on a very small scale a lot of new materials very rapidly. Now I'll go to the overall conclusion. So what are the goals we set out to achieve? We wanted to improve expandable graphite. We succeeded in that by finding these excellent binary compounds. We wanted to develop testing methods that can be used as a cheaper method, but also for rapid prototyping and using readily available materials, so that we could test a lot more material a lot faster. So what we found here is that our best overall result was with the low temperature expandable graphite mixed with EDAP. This improves the cost, it causes cohesive foaming, improves ignition resistance, it improves the resistance to mass loss, prolongs the time to failure, and pretty much covers the entire board on the minor, small, and medium scale of the improvements we desired in our fire retardant compounds. So now the question was, why is this combination so good? And that is because once we looked at the TGA, once we looked at a lot of our other results, looked at the thermal analysis results, we noticed that there was a very, very good, very close match between the degradation and the exfoliation events of the two materials. That together they created a very cohesive char as it covered the expandable graphite surface, which then reinforced its previous abilities as a thermal shielding barrier, and then possibly actually reduced mass loss even further because of that coating. And that is why we believe we achieved that synergism. We'd like to thank the following people in terms of funding and in terms of facilities. I want to thank the Department of Chemical Engineering at the University of Pretoria. Without them, I wouldn't have become the engineer I am today. I want to thank especially my supervisor, Prof. Kruger, and everyone at the Institute of Applied Materials that I worked closely with on all of these materials, that gave me some advice when we went for a coffee, that gave me some food for thought, and helped me to formulate my thinking so that I could continue thinking of new ways to assess our products. Then thank you to Prof. Brian Rand and Dr. Ncholu and the Saki Chair of Carbon Technology and Materials. Thank you for academic funding from the group to get the research continued. And also thank you to the National Research Foundation and the National Laser Center rental pool program at CSAR, which provided us with a lot of funding so that we could really dig into all of these results as we kept on going. Lastly, I'd like to do a few personal acknowledgements. I really want to thank the technical staff at the university who taught me all of the amazing techniques and helped me with how to approach the interpretation. I'd like to thank Dr. Ose Ofosu for his assistance with our cone calorimetry. Then Xyrus Technology and all of its staff, which really assisted with the production of the material, helped with the operation of the extrusion and the injection molding equipment so that I could really keep the ball rolling. And then I'd like to thank Washington, who sometimes worked with me on some of the laser results. And then last but not least, my wonderful students that I supervised. I managed to collaborate with some really, really great sharp young minds in Albertus, Albert, and Dievan, and we co-published all of us together, and it was a wonderful result. They delivered terrific work, and they've gone on to achieve some wonderful work since then, and some wonderful things since then. And with that, I'd like to thank you for taking the time to listen to the talk.